as I can back and forth. Okay. And actually, no, I'm going to insist on that. So you're going to do this for me, but I'll obviously put you in the right direction. So here's the problem I want to do. It's the basic problems that I've kind of been hinting at whenever I've been talking about this. The problems you're doing from homework are very similar to this. I think one's even the same mixture. Pentane, hexane, heptane, they're almost equimolar. Just easy to do it this way around the numbers. Being fed to a simple column, simple meaning one feed, two outlets. Saturated liquid feed. For now, we're going to send the reflux 2. And the goal here, and I want you to notice the unusual one. The goal, first off, is 95% purity of pentane in the distillate. And we want to have only 1% of the pentane coming out the bottoms. And then here's the obvious, unusual criterion is that we're going to have 0.499% hexane in the distillate. We'll play with that. I want to make a sheet where we can play with all of these and you can see what happens to the stages. Okay. Yes?
0.95%, 0.049%.
Do they not add up?
Well, is it supposed to be 0.95%?
Oh, I see. No, they're percentages. Sorry. Yeah, I think some percentages and fractions. I'm very sorry. Those are fractions. Those are percentages. That's just, it again, it's confused. I'll do everything in fractions on the spreadsheet, okay?
Can you kill that front row of lights?
Yep. Thanks. That one? Is that good? No, the other way. How's that? No? Okay. Go! How do I do it? Okay, I'm just, the big hint, of course, is do this as similarly to binary as we can. I'll give you another hint, start at the bottom. Okay, or just so we're all on the same page, we're going to deal with tie lines. We'll do tie lines. I'll spend 2 minutes making sure you get the tie line right. Let's just start at the bottom. So, before we get to starting in the bottom, what do we need to do? What did I do with the other one when I made the binary sheet? Yes? Yeah, sure. Okay, so let me just do this. F1, F2, F3. I won't ask for this. This is just the feed compositions, so this is 0.3, 0.3, 0.4. Let's put Q over here. Everybody see that? Should I make it a little bigger? Is that okay for now? Let's put ZD1. I'll come back. Okay. QR. Okay. What do I need to do next? So I think I've got all the inputs in. All right, I see it. So yes, I'm going to have stages. They're going to go in rows. Okay? But we can't do that yet. That's our goal, is to make it so that we can just have stages in rows. Before we get to inputting stages, okay, tell you what, let's just start with putting stages in rows. Okay? And you'll see what's missing as we do this. So I'm going to start at the bottom. Oh, and I can't type or spell. Okay. Let's do the reboiler, just like we did in the other one. Okay? What do we know about what's in the reboiler? Okay, I'm going to set this up. I'm going to do X1. I'm just going to give this part away, because otherwise I will be here for a while. Okay, so I'm going to have the liquid composition and the vapor composition. Don't get confused between the stages and the components. I suppose the easiest way to do this would be just instead of calling it 1, 2, and 3, to call it A, B, and C, and then you don't get confused. Are you okay with this for now? That I have components 1, 2, 3 and stages 1, 2, 3? Okay with that? All right. So here, yes, I'm going to step. So like the next, I'm going to have another line for stage 1, So I need to know the total vapor. Okay, I'm gonna add more, we'll get to that. I need to know the total liquid composition and total vapor composition. Do I know any of these values? Let's just start with 0. Don't worry about stage 1 yet. Don't worry about the second stage, we'll get there. This is 1, by the way. That's 2. This is stage 0 in the reboiler. What's the liquid composition in the reboiler? What do I know at the moment? I don't know much. Yeah.
Well, since you know that Q is equal to 1, the feed is saturated liquid, so wouldn't the liquid composition be just the feed composition?
Now we only know one thing about the bottom's composition. Yes.
You know the bottom, excuse me, I'm trying to say. You know you know ZB1, right?
Yep.
And then that's going to be the same as Y1. Because it's the same as Y1 for stage 1, right? Because aren't you gonna reboil and then it's in the same ratio, but it's the gas instead of the liquid?
Only when you're in infinite. We're not anywhere near that. We have a reflux of 2. Okay, so that's as far as I can get right now. Let's finish filling out the liquid. Yeah, that's it. That's all we got. Okay? What else do I need? Let's just start piece by piece. And this is where some of this a couple of steps actually are pretty straightforward. They're exactly the same as you did in binary. I just need you to step me through it so that I don't tell you how to do this. Yeah. Wait, hang on. Let's just go right here.
The reboil ratio.
So I got the reboil ratio. That's 2. Yes.
Use the equal slope equation, mass balance to get the other compositions.
Which is what? What is that? You can use that, but it's actually an easy way. What is that thing called? The lever rule, which is the, say it loud. It's the mass balance, yeah. Okay. So we can actually just do the mass balance. Okay? So what's the mass balance that we want to do here? First of all, let me put, do I need all of these? Do I need ZD1, ZD2, ZD3? Do I also need ZB1, ZB2, ZB3? Whoops. Do I need all of those? I need all of those, right? I need the distillate composition at the bottom. Okay? So do I know some of these? Yes. I know that this is this, and I know that this is that. Oops. Okay. What's ZD3?
1 minus.
Okay, so that's my distillate composition of heptane. Straightforward, right? Okay, this is all about just keeping things in order. This is like kind of like accounting. ZB1, again, I know that. It's given in the problem. Here's the problem. I can't find the other 2. Someone tell me a way to do that. Let's go to, you've already said it, so rather like, tell me how I'm going to do it. Almost new? You say mass balance. Okay, how do you do it? Go ahead.
Can you use the equation for the slope, find Z2B?
Go back 1 page in your notes or 2 lines in your notes. Before I start doing the slope, what were the equations that I gave you? Look at the lever rule. What's the lever rule here? Someone got it in the notes? You got it?
Yeah, can you do like Z2B minus Z2S over Z1B minus Z1F?
Yeah, which is equal to what?
What?
What's it equal to?
Z2D minus Z2.
Yeah, go back a little bit in your notes.
D over B.
There you go. Z over B, this is the lever rule. Same lever rule, just adds the i's, okay? ZIF minus ZIB over ZID minus ZIF. Okay, that's correct. Okay, you got the right, you're in the right place. Okay? Which component do I know all of those values for? You could pick any I, but you have to pick one. Pentane. Okay? So, how about if I do this? What's D over B equal to? D over B is equal to what? What's CIF? Do we know the pentane? Do we know the feed composition of pentane? I know the bottom's composition of pentane? If you do it like this, you can make it so you can adjust those and see what happens to the column. Do I know the distillate composition of pentane?
Yes.
Yeah. Oops, I need a parenthesis. And do I know the feed composition of pentane? Okay, these are all given in the problem. So that's D over B. If I know D over B, what can I do? So I can now, go ahead, yes.
Use the same equation for the other two components to find the composition.
Got it, let's just pick one. Which one do you want to do? Heptane, okay. Unless she has the other way, let's do heptane. Okay, so I'm now going to put in a 3 here, and so I'm just going to call this one thing D over B, okay? So I can say that Z3D minus Z3F times D over B is equal to Z3F minus Z3B. How many unknowns do I have there? It's just simple, right? I just want to make sure you keep track of, like, this isn't hard. This is just the mass balance. This is just the mass balance in this thing, right? I now know D over B. There it is. It's right there. 44%. Do I know the distillate composition of pentane? We're talking about pentane, heptane. Sorry, we're doing heptane. Yes? Do I know the feed composition of heptane? Do I know the feed composition of heptane? So the only thing I can find out the other one, right? So I can just bring this to the other side. I can make it so that this is Z3B is equal to, add that to that side, subtract that from that side. So it's Z3F minus D over B times Z3D minus Z3F. It's a nice simple equation. So I can say that ZB3 is equal to Z3F minus D over B times Z3D minus Z3F. Yes? Just mass balance. Everybody okay with that? All I did was the mass balance on heptane. And I get that. Now what's the bottom's composition of hexane? Okay, so now we know where everything is going. Okay, this is why you only need to give 3 compositions, by the way. Because everything else can be determined. It's quite straightforward, right? Yeah, yeah, go ahead.
So what you were saying before then is that now you have to do VLE to get the composition of the reflux stream. It's only
We're in the bottom. Okay, yeah. So I'm sorry. Yeah.
Yeah.
So let's just stay in here. Okay.
Okay.
Or if it's hard for you to picture a reboiler, bottom stage. Okay. We're gonna get the liquid composition, and to get the vapor composition is what? Not really, reflux is at the top. What do we need to get the vapor composition? You're ahead of me, but just I want to answer your question.
You need the operating line.
Not the operating line. What relates the liquid to the vapor in one stage?
Oh,
No, it's not. What relates the liquid to the vapor within one stage? Say it loud. Equilibrium. Okay? What relates the vapor to the liquid above it is the operating line. Okay? The easy way to remember which is which, because which one's the operating? Yes, the operating is because you always do mass balances between stages, but sometimes that's hard to remember. The easy thing to remember is within one stage, equilibrium. It's an equilibrium stage. Okay, so liquid and vapor in one stage is always equilibrium. That's the whole basis of this stuff. Okay? Okay, does that make sense?
Yeah, totally.
Okay. All right, I need one more thing. Speaking of operating lines, we're not there yet. What do I need in the operating line that we don't have? Say it loud. S. How do I calculate S? Yeah, go ahead.
Yeah, since you know D over B, you can relate that to D over B is equal to S plus 1 minus Q over R plus Q.
Good, nice. What's that called? That's right, you're right. What is it? It's got an easy name. It's the energy balance. It's a funny energy balance because we just cancel all the lambdas. Remember all that? But it's the energy balance on the whole column. Okay? So yes, let me write that down. Can I erase this? Everybody got that? That's all. I just use that to calculate the bottoms. Yes, anybody? So this is in the notes. This is just how to use it. So what was nicely told me at the back there is that D over B is the energy balance, is S plus 1 minus Q over R plus Q. Do we know all these values? We know all of them but S. Okay, notice we have to calculate D over B. We're given R and Q. So we can solve this and we get that S plus 1 minus Q is equal to D over B times R plus Q. S is equal to D over B, R plus Q, minus 1 plus Q. Okay? It's just algebra, I'm just solving for S. You can solve for Q, you can solve for R, but I'm solving for S. Okay, so I can put this in. Yes? So that's D over B times, let's, R plus Q minus 1 plus Q. If you do it all out like that, and leave the Q's and 1's in, notice that the Q and 1 cancel in this particular case. It'll allow you to solve the problem for a saturated vapor, just by changing Q. Okay, it'll change your feed quality. And then now it's robust. You can manipulate all those parameters and change it for any problem you want. Okay? Can I do this whole problem now? Does this seem a little bit more tractable all of a sudden? That header was actually just all the mass balances and energy balances, things you did in 120. But now you've done all that, we can do this. So someone tell me now, this is a little easier. So, what's x2 and x3 in the reboiler? Go ahead, you want to say it? You know? Yeah, okay. We just have these, right? It's just there. And there, correct? That's the bottoms, and that's what's in the reboiler. So there's the liquid coming out of this reboiler. Okay? Now we can go, okay? So now what's the vapor in the reboiler?
Now use the 100.
No.
You agree. I'm sorry, I was like,
No, I know, I'm sorry, I caught you off guard.
sorry.
Yeah.
Equilibrium,
Okay, remember what the equilibrium is in a
it's a summation of
the summation.
alpha times the component you're interested in, divided by summation of all.
It's the first thing we did in multi-component. Okay, so we need a little bit more information to put into this problem. What do I need? Yeah. So let's do A1, A2, and A3. And if you look up hexane, heptane, it's 6.35, 2.47, and 1, obviously. Okay? Okay? So now how do I do it? What's the first, let's do this a little easier, and let's just calculate this summation term at the bottom, right? Because we know all the liquid compositions, we know all the xi's, we know all the alphas. We just make the product so far. Yes?
We said that A3 is the alpha values. What is the A1 equal to like A13?
Yes, that by definition.
Alright, and then A2 is A23.
A23. Always to the reference, which is the heading. Okay? Okay? So obviously, the relative volatility between pentane and heptane is greater than hexane to heptane. Okay? How do I do that? Let's see if there's a simple technique for this. There is. Okay, well, let's do that. Okay, so I'm going to move this around a little bit, just to be, I'm going to show you a new command. Okay. If you haven't seen this command in Excel, this is just a little bit shorter. this the other way, is there's a term called sum product. And all it does is it basically does a dot product of two vectors. So if I do this vector and this vector, what it's going to do is it's going to multiply those two, add it to the multiplying of those two, multiply to the adding of those two. I use this all the time when I'm doing grades, because this is the weight and this is the scores on your homework. Okay, so I do some product all the time. Okay. So if you do that, then you get that. That number has very little meaning. All it is the numerator. Sorry, the denominator in this equation here. So all of the y's are now. So the pentane vapor composition is. If this is pentane, so now we're going to put a 1 there. It's alpha 1 x1. So it's this term times this term divided by the sum, right? And then if we copy this across, the thing that needs to not move is that purple one, okay? So let's make sure that this doesn't slide sideways. By $signing the H so it doesn't slide. And then as I slide it, it now gives me that correct. See that it's now doing the pentane vapor composition is the pentane liquid composition. Sorry, this is heptane. The heptane vapor composition is the heptane liquid times the relative volatility divided by that sum term. It's just that. So when you see this set looks really, oh my goodness, sum terms and subscripts. But when you actually use it, it's pretty straightforward, right? It's not very. So now I've got the vapor composition. Yes?
So in the textbook it said you only have to do it for the two like components. The sum has to include all three though?
Yes.
Or, okay.
Yes. So you only graph the two components.
Right.
So you still need to keep track of the, well, yes, you have to keep track of all of them because you need that liquid composition. You have to keep track of all of them.
Okay.
You just don't show the last one. Because you need that liquid composition there. You know it's multiplied by 1. Yeah, it's always going to affect that denominator. So you do need to keep track of it. Okay, now, how do I get the liquid composition in the next stage? How do I get the liquid composition here? Okay, so the operating line, did it change from binary? No, so the operating line is the same. But it has the i's in it. So let me show you the operating line, the bottom operating line. Again, this is just look at your notes. It's nothing, I'm not doing anything new here. Yin is equal to s plus 1 over s xi n plus 1 minus zi b over s. Okay? So let's make our lives a little bit easier and define this as s. Okay? So that's now s. And now let's go here and do the liquid composition. And it's just, okay, so what's the problem here? Yeah, go ahead.
We don't have a value for just B.
It's just B? No, sorry, this is Zi, comma B. They're both subscripts.
Oh, okay.
It's the bottom's composition of whatever component. Okay? No, I got it. It's my handwriting. I'm sorry. So what do I do? What's the thing that we did in binary when we had to do the stripping part of the column? Go ahead and say it loud.
Solve for S.
Solve that for x. Okay? It's not hard. So we're going to multiply by s. So we get s, y. I'm just going to drop the subscripts while I'll do the algebra for my life easier. S plus 1, x minus zb. And so, I'll do this out. S, y plus zb is equal to s plus 1, x. X equals s over s plus 1 y plus zb over s plus 1. Okay, now to put this back, this is x, I, n plus 1, I, n, The liquid composition is just this function of the vapor composition in the stage below. So n+1, if we're interested in stage 1, it's related to the vapor in the stage below. I won't go through this because it's exactly what we did for binary, right? We just do mass balance, equilibrium, mass balance, equilibrium. And so to implement this, it's now just equals S divided by S plus 1 times Y I. So this is the pentane vapor composition. This is the pentane liquid composition. Plus ZB of that component, which is that one right there, divided by S plus 1. Okay? If I copy this across, it should be correct. So notice that this is now the hexane liquid composition, the hexane in the bottoms, the hexane in the vapor, one stage beneath. Now, how do I know this is all right? How about if we just put a little check in here, and we'll see is if these all add up. Are those values at least make sense? And I'm just going to cheat. I'm just going to then slide this over like that. Do those make sense? Are all those vapors correct? And similarly, to all of those x's make sense at least. Okay? You don't even need to do it. There's no solver. This is just, does this make sense? Looks like it's making sense. Now how do I get the vapor compositions in the next stage? Now it gets a little easier, right? Can I drag down?
Yeah.
No? I need to do all of these, right? So let's see, this probably didn't work right. So I have to make sure that these all the 7. So what happens is you shift it down, so the 7 needs to be star. Okay, so now when I drag that down, that's correct, but then something's wrong here. So this one also needs to not move. No, not there, sorry. When I copy this down, notice it's still, I want to still reference the right alpha, the right sum, and the right x. Okay, so I want x to move, but I don't want alpha to move. It may take 5 minutes to play with that, okay, and then you'll understand what I'm doing. Because it's this next step that you'll appreciate, okay? Yes, it took me 5 minutes to think that out. Well, I knew what I was doing, so I did it in 30 seconds. You'll think about it in a few minutes, okay? Do those vapor compositions make any sense? Yeah.
One thing, I don't know what you did here, but I think you used the ZB, and the ZB is going to change every time you drag it down.
You mean here?
No, for the X's.
Yeah, okay, so you mean here, so I have to fix that. Yep. I was going to do it as I saw it messed up, but that's fine. I was going to just debug, do it and show the debugging, but that's fine, you're right. So what he's saying is this one also needs to be fixed, so let's just fix it. It's ZB doesn't want to drag down, okay? So let's now make a whole lot of stages, and with ternary, you don't have to worry about switching. You're just going to show the whole profile. Okay, so go all the way to the feed pinch. Remember I told you just go to the feed pinch? So let's just make a lot of stages, and what you'll see is at some point this will stabilize, and the compositions won't change. See, it's about there, okay? It's about the same. Small changes there. Okay? So this is the feed pinch composition, somewhere around 0.42, 0.28, 0.29. That makes no sense to you right now. Okay? Let me draw it so that it makes some sense. Okay, so we're just going to draw x1 and y and x2, and this is actually quite simple. We're just going to take this, we're going to graph it. Always use a scatter plot. Okay, now that doesn't look very good right now, but we can fix it. We're going to fix it the same way we fixed the other one. First, let's insert an object. So I want to make it square, remember? So let's make a nice square diagram. Okay. And is this the right range? Number one, let's get rid of these. Always just get rid of these bars, okay? So get rid of those. What should this go to? 1. Let's just force this to 0. Okay, let's have this go to 1 and 0. Okay. How am I going to put in? I'm going to get rid of this for now. No, let's not do it. Okay. How can I put in the diagonal of this triangle? Yeah, Nathan, yeah, good.
It's gonna be 0, 1, 0.9, 0.1.
Yeah, you don't have to be that, it doesn't have to be that complicated. Let's just put in, let's just go, it's going to be at 0, 1, and at 1, 0, right?
Yeah.
Okay, so if we go to this chart, and now we're going to add some data, select data. We're now going to add some, and the x values are these, and the y values are those. How's that? Okay, so of course we don't want to have any points. We want it to be black, so you can't tell what it's. So we're going to say it's a solid line. We're going to make it black. Let me get rid of the markers. Make it black. Make it black. Oh, it makes all these gray nowadays. Okay, so let's okay, how's that look? Does that look a little bit like what I drew in class? Okay. So, how am I doing? We are till 5:30, right?
Yeah.
Should we make the rectifying so you can see both of them? So we're going to start at stage n plus 1, because that's the distillate. Then we're going to have n, whoops. Then n minus 1, then n minus 2, etc. Okay? And we can actually have, it'll just do this. Whoa, that's not right. Okay, so now we can have our top column. Let's have again, let's just take this whole thing and just repeat it. What do we know about the top stage, n plus 1? If we want to, what do we know about that top stage? Yeah, right. Whiches, you're correct. The liquid or vapor. In this stage is the vapor of the liquid that's equal to the distillate.
That vapor is
Yes, right. Okay, so we know, what I'm gonna do here is I'm going to, here's another little trick. I'm going to make a split screen. So now I can scroll down. See all those values?
Witchcraft.
That's actually, that's making it here. Okay, so now I don't have to do all that. Okay, so I know. Okay, view, split screen, split right there. Okay, you can also do freeze frames, works pretty well too. You can actually move this now as well. You can click it. But now you have two screens. You can scroll this one. You can also scroll this one. It just depends on where your cursor is. Okay. But I want to have it so I can see my top header and this part I'm working on below. Okay. The vapor composition is equal to what? We told us it's a distillate. Okay. So we know that it's equal to here. Here. Good question. It's N. So it's the top stage. Leave the N plus 1 for just a second. Okay? I'll come back to that. Right? Because this is stage N. And the vapor here is Yn. And of course, this is also still Yn, which is equal to Zd, because it's all condensing. Okay? So now how do I get the liquid in stage N? If I know the vapor in stage N, how do I get the liquid composition in stage N? Say it loud. Equilibrium. Okay. Can I use that? Now, say loud. You got it. You know it. There's another equation in the book. Okay. So if you look at the book, there's another equation here, and it only works when what? Do you know what the little asterisk on this equation is? It's what? Constant relative volatility. So you can't actually invert. It's easy to invert algebraically when it's constant. Okay, but it's not constant. You can't invert it. But if you look, it's not in the notes, so you might want to pull this out or write it down. But the inversion of this is just xi is equal to yi minus alpha I over the sum of yi's over alpha i's. Okay? Can't use sum product here. What did I do? So did I have a trick for it? No, no trick. Okay. So in this case, I just have to do that sum. So it's just vapor of each divided by the alpha. So it's this one, just bear with me as I type this in. It's equal to this one divided by that one, plus this one divided by this one, plus this one divided by this one. Okay? And I don't want the denominators to move, so I can where to fix these is just, the best way is just to do trial and error. Okay, so then each of these is just going to be equal to the y divided by the alpha divided by this sum. Okay, now I should be able to copy this over now. Okay, so it's y divided by the alpha, y2 over alpha 2 over the sum, and if I move over, let's check that it's right, it's the vapor composition divided by the relative volatility divided by the sum, and do these make sense? They do, okay. So now how do we find the next liquid composition? So now we've found this vapor is a distillate. This liquid we get by equilibrium. Now in stage n-1, how do I get the vapor composition here? Okay, top operating line. The top operating line in a multi-component column. yi n minus 1 is equal to r over r plus 1 xi n plus zi d over r plus 1. Okay, so this is just, to do this, we're just now going to do I can't call it R, I don't think it lets me call it R, so let's do the same thing before, we'll call it RR. Times that X composition plus ZD now is this Y composition. I want to make sure it doesn't move. Divided by R plus 1. Okay, so now we should be able to copy this over. And we should be able to now copy everything down. Oops, something down. Okay, and we'll see if everything's correct. Yep. So can we just copy this down and go towards the feed pinch again? I just did the same thing as before, right? Nothing new. So let's just go down to the feed pinch. Do we see that the compositions stabilize? Do they get stuck at one spot? Okay, there's our feed pinch. Not quite there, okay. Why did I leave, we don't really have a stage n plus 1, doesn't really exist. Why did I have to put that there? What's the first point? When we do our mass bounce, when we like connected the feed, the bottoms of the distillate, does it connect to the liquid composition here? The mass balance on the whole column, does it go to this liquid composition? That's here, right? This liquid composition is the liquid in the top stage. But when we do our overall mass balance, our lever rule, do we go to that composition? We go to where? Distillate, which is the vapor. So just for graphing purposes, so I don't have to add one extra point, I'm just going to have this arbitrary, this is just for graphing, okay? This is the one little bit of graphing I'm going to do. I'm just going to say this is equal to this. And this is equal to this, and I don't need the third because I just need to graph the first two. It's not really a liquid of stage n, it's just a tie line, okay? Making it draw the dotted line, you could, it's a bit of work. It's also not worth it, okay? But here's the point to remember. This is the liquid in the top stage. This is the vapor in the top stage. You're putting this in just so that the line goes to the right place. Does that make sense? Remember, we got to get to 95, that's our goal, okay? So it'd be nice to show it on the graph. All right, so let's just add this in. Let's go back up to this graph. Let's add in our new data. Add x. And then here's our x values. And our y values. Notice that y, don't get confused. In this case, y is x2, okay? We do have y's, but y is, it's x1 versus x2, okay? So don't get confused with the names of things. Excel forcing you to call it that. Now, what does that look like? Well, let's make that a better color. All right, let's just, okay, so, let me get rid of my split screen. I'm just going to move this over so now I can change all my parameters. Do you see how this is working? This is now the distillate composition. This is the liquid composition in the top stage. Going towards my feed pinch. This is my bottoms composition going towards my feed pinch. Remember that existed in binary as well. We also had feed pinches in binary. Okay, so this column is going to be this bottoms, first stage. This is the this is the reboiler, is the first stage. So it's reboiler, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is just a tie line. So so 12 stages. And yes, you just count it off. No, you can't do it with a ruler. You need to do that, you have to do those summation terms, okay? You could do it with a calculator, it would take you some time. Think about all those summations you have to do by hand. You could do it, it might take you, and then if you made any mistakes, it'd be frustrating. Excel's really nice for this, right? This is what Excel's built for. Yeah.
So when you're using Excel to find R min,
Yeah.
so do you just adjust your R value?
That's great, let's just do it, okay? I have 4 minutes, so I want to show you a couple things. I want to show you first the saddle pin. Well, let me show you the arm pin first, and then I'll show you saddle pin. Once you build this, there's a lot of things you can kind of be like, I've been talking about in lecture, that makes sense, okay? And it just comes out of the math. Did I do anything strange? All I have is equilibrium, energy balance from R to S, and operating lines, exactly like binary. All I'm doing, and if you want to see it, there's the vapor compositions. They're there. Notice we have to calculate the vapor in each stage in order to get the next X. We just don't show it. It's just that it's not shown. Does that make sense? Does this make it a little more clear what those diagrams were? It's just only showing part of the information. Okay, so now, let's start reducing R. Does a reflux of 1 work? No? Okay, easy. Okay, so R min's got to be somewhere between 1 and 2. Let's try 1.5. I don't want you to know what the answer is here. How about that?
A little smaller. So it's just, like, because that's what I was confused on, it's just when they cross.
It's just when they touch.
Okay.
And what you'll find is if you do Underwoods, now remember, Underwoods optimized that composition. So this is finding R min at a fixed hexane. So Underwoods is now saying, okay, let's make this optimal so that we get the R min. Let me show you how R min affects that. If I now change that ZD2, if I make this just 0.04, okay? So I'm putting a lot more heptane into my, let me show you where we're at. This is 0.95, right? This is 0.95 to here. So I'm not changing the purity of pentane in my distillate. My pentane is 95% pentane. Not changing anything. By moving up and down here, this is where you have to not get confused by numbers, where graphs are so much better than numbers. Because graphs allow you to see everything in their totality. By going down a little bit, we're now adding a little more heptane into my distillate. Does it matter? Not really. Well, let's see what happens when I add a little bit of heptane into this thing. Okay? Does that reflux work? Can we use 1.3 at that level of heptane? Okay, so what is the minimum reflux at that heptane? We have to put a lot more energy into this thing. Does a reflux of 2 work? Does a reflux of 4 work? Does a reflux of 10 work? Okay, see what I have to do to the reflux in order to get that much pentane to go into the distillate? Heptane, to get that much heptane into the distillate. But do you care about getting a lot of heptane? And all we did was go from 0.001 to 0.00001 to 0.001. Okay? So basically I added 100 times more heptane into the distillate. And to do that, it cost me 10 times as much. But do you care? I don't. It's still an impurity, okay? Do you see what I'm saying? That's why when you do Underwoods, it optimizes this. Let's try making even less. Instead of making 0.04, let's do 0.049999. Let's make it so there's very little heptane in there. Okay. Did a reflux of 2 work? Does a reflux of 1 work? Not quite. 1.2, it's a little better. But now this is a vanishingly small amount of heptane, and it uses a little bit less energy. Not much, but a little bit. Do you see the dependence on R and heptane composition? And am I changing the purity of my product? No, it's all 95% pentane. Okay? That was our min. Saddle, can you begin, you see the saddle here? So let's start diminishing ZB1 so you can see the saddle. 0.001. Watch it start to go toward that edge. Okay? In my stripping, which is the blue line, at the moment I have 21 stages. Okay? And it's still going towards a feed pinch. You see how those are the same? Okay? But watch what happens. At some point I'm going to have to add more because that saddle is going to consume all my stages. And I'm going to have to add more stages. Okay? So let's do 0.0001. Okay, do you see all the stages that now are going in there? And that's just by saying, letting a little bit of pentane go into my column. notice that now, that saddle, it's still feasible. I'd have to add more stages because it is coming into the column, but this is now 10 to the minus 6 pentane. So somewhere between 10 to the minus 5 and 10 to the minus 6 starts making this very costly. So what difference does that make? How much are you wasting? It's not very much if you think about it. Does that make sense? You're not losing that much pentane. Between, if you're thinking about like 1 part per million versus 10 parts per million. And most of it's coming out of the distillate anyway. You see that? Oops, not there. See that? It didn't like that either. And there's going to be another one. There's a limit to how far you can push that distillate composition. If I add too many 9s here, I'm also going to get a saddle pinch. See that? See now this saddle pinch is now consuming a lot of my stages. But even that, look at the purity here. If you look at the amount, this is 10 to the minus 10 heptane, and yet it's still functioning. Okay? So in other words, this column really doesn't like having heptane for distillate. Okay? You need a little, but very, very little. Okay? Do you see how you can play with this and learn a lot just by playing with these numbers? You make it robust enough so you can just change numbers. You can see what's happening. Kind of, yes? See how it's still a useful plot, even though it's not on a capability. Question? Yeah, but let me just answer a couple questions, and I know I'm running over 2 minutes. Yes, was there a question?
Never mind.
Okay. Let me ask this question back to you. This was a long question. Could you make this? Is this straightforward? Not easy, straightforward. Can you do it step by step? Nice accounting methods, okay. Is it useful once you make it? Can you see how this is a useful thing? Okay. And if you ask me the question, I'll tell you, no, you can't make this on an exam. Okay? But you do need to understand what's happening here. Okay? All right, thanks very much. This should help you with your homework, obviously.
That's what he's saying. Put a picture